Okay, hello everyone. Uh, in this movie clip, we are going to study some non-ideal effects such as breakdown mechanisms to be occurred in BJT device structure. Afterwards, we are going to define Gummel plot, Gummel numbers to quantitatively evaluate the BJT device performance. Afterwards, we are going to learn and take a look at the cross-sectional view of modern BJT device structures and followed by base transit time as the last topic of this lecture. So in the very first movie clip, I'm going to briefly tell you the BJT breakdown mechanisms as the first step. So please take a look at the sentences written onto the lecture note herein. In the common emitter configuration, so emitter electrode is used as a common electrode. It's kind of grounded. The emitter is grounded, so that base is input and collector is output. Okay, so this is a very conventional and typical configuration for BJT to be used as an analog amplifier. But the question is, what if the output voltage in this common emitter configuration, the output voltage is defined as emitter to collector voltage difference, and the output current is defined as a collector current, right? So what if the output voltage is very high? Then, you may expect that output current should be constant in common emitter configuration. If you're not familiar with the BJT, then go back to the MOSFET, planar bulk MOSFET, and the MOSFET is now under, saturation mode, so that output voltage is drain to source voltage and output current is drain to source current. So for given gate to source voltage, the whatever how high or how low the drain to source voltage is, which is output voltage is, the output current, drain source current should be saturated, should be constant. But what if the uh, VDS is very, very high? Then can you still expect very saturated IDS current in your MOSFET? No. In the end, the MOSFET will be broken down. Similarly, in BJT, if in the common emitter configuration for a given very high output voltage, which is a high V sub EC, your output current of BJT wouldn't be saturated. In the end, it would increase. So take a look at this figure on the right hand side. The I sub C, which is the output current, and x-axis is V sub EC, which is the output voltage. So when the output voltage is very small, maybe in this regime, your output current is more or less constant. But take a look at VEC is VEB plus VBC, right? And this in the common emitter configuration, this voltage difference between emitter and base is constant, right? I mean, for a given gate voltage, you should measure the drain current versus drain voltage in your MOSFET. So same thing, same output voltage characteristic are given in this lecture note. IC versus VEC. But here in the VEC consists of VEB plus VBC, but in the common emitter configuration, this VEB should be constant. Therefore, while you are varying the VEC value, which is equivalent to varying the VBC voltage, okay? But what is this value? What is the physical meaning of this value in your PNP BJT? Base, right? And the collector. So in this NP junction, I mean the collector junction is now reverse biased, right? In common emitter configuration. So when VEC increases, I mean in this direction, if your VEC increasing, keep increasing, which is equivalent to increasing your VBC. So if VBC is increasing, then your collector junction, base collector junction is more aggressively reverse biased. Then let's go back to your PN diode theory. Under reverse bias, Saturation, the current reverse biased PN diode can flow very tiny amount of saturated current. However, if your reverse bias is too high, I mean the beyond the breakdown voltage, your reverse biased PN diode can flow exponentially increasing current across the PN diode. Similarly, in this the PMP BJT device, your base collector junction is under super reverse bias. Then you may expect the breakdown events to be happened in this base collector junction. Then this physical breakdown event would give us this ever increasing output current versus output voltage. Okay, so herein, how come the IC current is increasing as output voltage is increasing? Why this current is increasing? The answer can be found that your PN diode has been broken down. Then let's go back to the PN diode theory. What kind of breakdown mechanism that we have learned for the PN diode under reverse bias? Yes, two mechanisms we have reviewed. Punches through, and the other one is avalanche. Okay, so punches through would be happen the first. Afterwards, avalanche breakdown mechanism will be followed. So in this output characteristic plot, this part, the current output current is exponentially increasing, right? So this part, how come the output current is exponentially increasing? Because of avalanche breakdown. And how come the output current is monotonically increasing as your output voltage increases? The physical origin for that comes from punches through event. Okay, so now if you have any chance to measure your own BJT device, I mean, maybe when you have a job in industry, your job responsibility is to monitor the output characteristic of BJT device. Then at some point, at a very high output voltage, I mean the emitter collector voltage difference is too high, then what would be happening in your output current IC? Yeah, you may expect this output characteristic plot. Okay, then let's do analysis for that. Okay, number one is punches through. So what is the punches through, by the way? Punches through means no cause and neutral reasons to be left behind because of the extended out depletion layer coming from junction, metallurgical junction. So punches through is you mean in the case of PNP-BJT device, in the common emitter configuration, this hole has been injected into the base region and is going to be diffused out toward the collector region. So if these injected holes are successfully going throughout the quasi-neutral base regime, then we may expect that very saturated output current for given output voltage. However, what if your output voltage is too high? I mean, again, VCE is very high. Then, since VCE is a VCB plus VB, no, V, no, sorry about that. VEC, it should be VEC. So this is a PNP. So your output voltage VEC is equal to VEB plus VBC. And since in common emitter configuration, VEB is constant, right? As I have just told you in the previous slide. So you're actually increasing VBC. So if this VBC has been increased, then take a look at here. This depletion layer coming from the collector base junction. So sorry about this, it should be typos. Collector base depletion region and the emitter base depletion region, this guy, the black colored one, this emitter base depletion region. So both those two depletion regions would be touched together. Where? Yeah, in the base region. So take a look at here. The quasi-neutral base region, the width, physical width of the quasi-neutral base region defined as or denoted as a W would become 0. When? Yeah, if your output voltage becomes super high. Okay, then we can call it, yeah, punches through has been happened in the base region. Okay, so the definition of punches through in BJT is emitter base and collector base depletion region. Those two depletion regions are touched together where in the base region. Okay, then we can say that the W, which is the physical width of the quasi-neutral base region, is becomes zero. Okay, then what is the physics behind it? So this is a emitter, this is a collector, that is base. And in the common emitter configuration, emitter base is forward biased and base collector is reverse biased. So this is P type, this is N, this is P. So for this given PNP BJT device, this PN diode is under forward bias. So that is Fermi energy level in emitter side, and in the N side, if you remember how to draw the energy band diagram for the PN diode under forward bias, that would be like that. Okay. Then on the right hand side, let's draw another energy band diagram for the PN diode under reverse bias. So this is a P side conduction band edge, and that is a conduction band edge in the N side under reverse bias. So the reverse bias means the P side has been moved upward and the N side has been moved downward. So if I connect all the conduction band edges, then you may draw the energy band diagram for this PNP BJT device. Again, the first junction, emitter base junction, is forward biased and base collector junction is reverse biased. Okay. Then now take a look at how the holes can be injected into the base and how they are moving toward the collector side. So take a look at the hole in the emitter side. Since this emitter base side is forward biased, so that the energy barrier height for holes would be lowered. So many holes would be injected into the base. Once hole has been injected into the base, since punches through has been happened, so that there is no neutral region in the base. No neutral means no flat or no flat energy band diagram in the base. So once hole has been jumped into this hole or kind of an energy potential hill, then hole can be slide down. Okay, and this part comes from the very high reverse biased PN diode. So previously we talked about that once you find out the banding in your band diagram, there should be built-in electric field happened. Okay, so electric field has been now applied along this direction, along x direction, so that the hole would be drifted toward the collector side because of the electrostatic force, Coulombic force. Okay, so hole has been now moving, accelerated, but since there are many silicon atoms here and there, so because of the phonon scattering, the injected holes from emitter would be hit the silicon atom or vibrating atoms or phonon, so that it's going to lose its kinetic energy. So in the end, the hole would becomes like that and accelerated again and get kinetic energy. Afterwards, it's going to hit another silicon atom and it's going to lose its kinetic energy, but still the built-in electric field is available, so it is going to re-accelerate it again and hit the other silicon atoms and lose its kinetic energy. So in the end, it's going to be arrived at the edge of the collector region. So this is a bottom line or base fundamental physics, how the injected holes can go through the base regime because of the built-in electric field. But how come the built-in electric field has, governed throughout the whole base regime? Because a punches through has been happened. In other words, no quasi-neutral region left behind in the base region. Why? Because you have applied a very high output voltage for your PNP device. Okay. All right, this is the mechanisms. How come in your output characteristic plot, IC versus VEC, why your current is keep increasing monotonically as your output voltage has increased. All right. The second one is avalanche multiplication, avalanche breakdown. So, I mean, I'm talking about this part. How come the output current is not monotonically increasing, but exponentially increasing? Why is that? There should be another physics. So the answer is avalanche breakdown event. So when we have learned the PN diode, we have thoroughly reviewed the avalanche mechanisms. So I guess we don't need to go uh, in detail. However, briefly, let me talk how avalanche has been happened in this PMP BJT in common emitter configuration under very high output voltage. Number one, yes, holes from emitter are injected into the base. So I mean those three holes are now injected into the base. And then in the end, once not too many recombination has been happened in the base region, then these holes would be arrived and get into the depletion layer between base and collector. Okay, and then holes are collected by the base collector junction. So some holes in the base collector region would have a sufficient amount of energy to generate electron hole pair. I mean, if your output voltage, go back to this slide, if your output voltage is very high, 80 volt, 100 volt, like that, then your bending is more. So that for a given acceleration or given you know unit lengths that this holes has traveled, uh, the total amount of kinetic energy to be lost is very high. So if this kinetic energy to be lost is higher than 1.5 times band gap energy of silicon, then we may expect another electron hole pairs to be created because of this lost kinetic energy. This lost kinetic energy can be well delivered to the electrons, which was well stabilized in the covalent bonding between two silicon atoms. Okay, so because this kinetic energy to be lost is very high, like 1.5 times the band gap energy, then we may expect additional electron hole pairs. Then at this position, one hole can induce one additional hole, so that total number of holes available at this position is 2. So one hole can create two holes, and these two holes would be accelerated again because of this built-in electric field. So that two holes would induce two additional electron hole pairs. So in the end, four holes would be created. And those four holes would be accelerated again and induce another additional four holes, total 8, right? So that 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, like that. So exponentially, the total number of holes created within the base collector depletion layer would be exponentially increased. This is the main physics. How come the avalanche events can be happened then? How come in your output characteristic curve, your output current I sub C has been exponentially increasing? So it's a kind of internally created electron hole pairs are the main driving force. How come your exponentially increasing output current can be observed and monitored and measured in your measurement tool? All right. Then I guess I have already explained it here by this. And let's take a look at how the generated electrons, not holes, generated electrons can be traveled in throughout this PNP diode. So I'm talking about this. Once EHP electron pairs are created, then electron would be moved toward the emitter side because a built-in electric field has been formed in this direction. So electron has been accelerated and due to the phonon scattering, it's going to lose its energy and move, lose energy, and like that. So in the end, it's going to be arrived in the base region, and because this PN diode has been forward biased, so once electron has been well arrived in the base region, it is more likely to be injected into the p side because this is forward biased PN diode. So by event 4, you may expect that some additional electrons would be supplied into the emitter side. So once each injected electrons injected into the emitter side would result in the injection of IEP over IEN holes from the emitter into the base. Okay, so that once this additional electron has been supplied here, then the potential here would be lowered and more additional electrons would be supplied into the base collector junction. Then once this potential here has been well suppressed, well lowered, then many holes would be directly supplied into the base collector junction, and it's going to be the main physical origin. How can the avalanche multiplication has been happened? Okay, so carrier multiplication in the collector base depletion region is internally amplified. I mean, internally, not externally, but internally. Why is that? The bottom line, uh, origin is electron hole pairs. Okay. All right. So we have gone through the BJT breakdown mechanisms. So again, there are two mechanisms: punches through and avalanche. Okay. All right, let's switch gears slightly and take a look at the non-ideal effects in BJT. So let's review and think about the non-ideal effects in PN diode. How many non-ideal effects did we learn? Breakdown, right? And generation current, and recombination current, and what else? Yeah, series resistance, high level injection. Okay, so if you're not familiar with it, or if you forget those non-ideal effects in PN diode, please go back to the PN diode movie clip and review it. Now we are learning the BJT. BJT is, two PN diode has been connected together, right? So when it comes to the non-ideal effects in BJT, well, you may reuse the non-ideal effects studied in PN diode. Okay, so one of the performance fact metrics in your BJT is emitter efficiency, gamma, right? So take a look at this gamma. So gamma was defined as how many emitter, no, how much the portion of emitter current by hole uh, divided by total emitter current. So the maximum value of the emitter efficiency is 1. So we would like to have IEP is much higher than IEN. So for that purpose, uh, emitter side should be very heavily doped and the base side is relatively lightly doped. So P plus N junction is necessary to achieve very high emitter efficiency. In common emitter configuration of your PNP BJT, your emitter and base side is forward biased, right? In common emitter configuration, right? So once this PN diode is under forward bias, then what kind of non-ideal effects should we take care? What is forward bias? This PN diode is forward bias. So go back to the current versus voltage plot of a single PN diode under forward bias. This is an ideal one, but real measured data said this. So, but I'm talking about not very high uh, emitter base collector as described here at very low emitter base voltage. I mean for a given single PN diode, if you are applying very small forward bias, here, then why this difference has been happened? What is the physical origin? Yes, recombination current. Okay, so recombination current has been happened in your forward biased PN diode. Why is that? The electrons in the N side and holes in the P side, but uh, the energy level of those electrons and holes are quite low, not enough to go over this potential energy height. However, once hole and electrons are recombined in the depletion layer, then we may expect one more additional current pass across the PN diode. That was the recombination current component to be measured in your PN diode at very small forward bias. Same event would be happened in your PNP BJT as well. In common emitter configuration, your emitter base junction is small forward biased, so that total amount of emitter current is not these two components, but one more thing, that is recombination current. Herein, just for your convenience, I have written down I sub RG, but IR is the exact one. So recombination current has been included in this part so that your emitter efficiency would be hurted because of this recombination current. Okay, so in ideal transistor analysis, ideal BJT analysis, thermal recombination generation current in the emitter collector junctions were neglected. As we have done in PN diode, we have ignored thermally created recombination generation current in the depletion layer of PN diode. Yes, similarly, in PNP BJT diode analysis, PNP BJT analysis, we should ignore the thermally created recombination generation current. So under active mode operation with small forward bias, the emitter base side is small forward bias. So thermal recombination current is likely to be a dominant current component of the base current, which results in the very low emitter efficiency, which is bad news for BJT to be used in analog amplifier. So in the end, hence, lower gain is expected. So this non-ideal effects happened at very small forward bias in BJT. At low VEB, emitter base voltage is very low. And so this limits the application of the BJT for amplification at very low voltage. So we would like to have a very low power device, low voltage device for mobile applications. Then you may catch this idea. Aha, BJT is not a good option, not a good menu for low power mobile applications. Okay, so that is the main reason why plain bulk MOS FET has been widely adopted for mobile applications. Okay, so I guess the time is okay. In the next movie clip, I'm going to begin with another non-ideal effects at very high emitter base voltage. So see you in the next movie clip. Bye bye.